In today's video, we talk about the theories behind why reaction rates behave the way they do. What we've been looking at so far with differential rate law and integral rate law is empirical. We just observe what happens and fit laws to the phenomenon. But scientists, of course, are always interested in knowing the why behind the what, and that's what these theories that we're going to look at today are about. The big theory is collision theory. And the idea here is that reactions go faster when there are more effective collisions between reactant particles. We've already sort of generally looked at the idea that reactions go faster when the particles can meet, but how specifically at the molecular level or the submicroscopic level are reaction rates affected by these collisions. Collision theory basically says the rate of reaction is proportional to the number of effective collisions that happen between reactant particles per unit time, per second or per minute or whatever. So what makes a collision effective? We're going to look at two different factors that have to do with how effective a collision is likely to be. The first one is orientation of the molecules. Take a look at this little animation. What you just saw there was a collision that was not effective. The goal of this reaction is to react these two particles to end up with the two green atoms combined as a product and the two red and the blue atoms combined as a separate product. Because the particles were oriented improperly, like this collision did not occur so green was to green but green was to red, that orientation made an ineffective collision. Reorienting the particles like this would make a more effective collision, because the correct particles impact each other and can provide the overlap needed for the time needed to generate new bonds. The collision was an effective collision and the reaction occurred. The more particles collide with correct orientation, the faster the reaction is going to go, and that sort of makes sense. But even with proper orientation, it is possible for reaction rate to be relatively low. So look at these two particles collide. Their orientation is correct, but the collision is still ineffective. The difference between an effective collision and an ineffective collision when orientation isn't a factor has to do with the molecular kinetic energy. These particles impact each other because of the speed that they carry into the collision. If they're moving faster, they collide more deeply, and then a reaction is more likely to occur given that their orientation is correct. So molecular kinetic energy is a factor here. The way we talk about this is in terms of something called activation energy. This graph has something called reaction coordinate on the x-axis, and reaction coordinate is something like distance through the reaction, sort of. It could be thought of as time if the reaction is happening at a steady pace. And in the y-axis, the vertical axis, we have potential energy. The reactants have a certain amount of potential energy. That's a starting point. The products are going to have a different amount of potential energy. That's an ending point. And the difference between the two energies that are stored in reactants and products is just the delta H for the reaction. This happens to be an exothermic reaction because we can see that there's a loss of stored energy from reactant to product. But in between, what happens is there's a little energy hill. And the reactants have to gain a significant amount of potential energy in order to become products. This is very much like a hill that you'd have to push a rock or something up to get to the other side. The difference between the energy stored in the reactants and the potential energy at the top of this hill is what we call the activation energy, or EA. At the top of this curve, for a very brief instant in time, there exists an unstable species. It's a transitional species that's called an activated complex. It's not product yet, and it's not reactant anymore either. It's the middle of the collision. It occurs right at the top. And if your reactants have enough kinetic energy to overcome the activation energy, form an activated complex, and then decompose into products rather than reactants, the collision will be effective. Endothermic reactions are the same way. Delta H is positive. but the activation energy is still the difference between the energy of the reactants and the energy at the top of that energy curve where the transitional species, the activated complex, exists. If you had a reverse reaction, EA reverse, sometimes this is called EA prime, would just be the difference between the energy of the products and the top of the energy curve. So why are some collisions effective and some collisions are not effective in terms of kinetic energy? The particles fly together. So here's particle 1, here's particle 2. They move toward each other and they have a certain amount of kinetic energy. So kinetic energy of particle 1, kinetic energy of particle 2. They move toward each other and they collide. At the moment they collide, they stop moving. So all the kinetic energy that was in particle number 1 and in particle number 2 has now been converted into potential energy as these particles have been smushed together and their electron clouds, the orbitals, have been overlapped into each other. So kinetic energy at the top of the motion, at the end of the motion, is 0. It's all been converted to potential energy. Now in this diagram, the kinetic energy, when it's converted all into potential energy, is enough to get to the top of the curve. That will be an effective collision. Here's a different situation. Particle 1, particle 2 fly towards each other. KE1 and KE2 are both converted into potential energy, but at the moment of collision, when the kinetic energy has all been converted into potential energy, it's just not enough. It only gets this far up the hill and doesn't make it to the very top. So you'd start out with reactants, go up the hill, but you wouldn't make it, and you go back down. The activated complex would never form, and you would never make products. So the particles have to start out with enough kinetic energy to get over the activation hill and become products. Well, we know that kinetic energy is directly proportional to temperature. In fact, that's what temperature is. It's a measure of kinetic energy. So we could expect that for all reactions, higher temperatures should give higher reaction rates because more particles would have sufficient kinetic energy to overcome the activation energy and then react. On a frequency diagram, like we saw when we studied solids and liquids, this is what that would look like. Here are two different temperatures. This is a low temp. This is a high temp. The blue curve, the low temp, shows a shaded area that's shaded in kind of purple here. I'm reshading it in green. That's the number of particles that have energy that's bigger than the activation energy. So this dotted line here represents the cutoff, the activation energy needed to cause an effective collision. That's how many particles would effectively collide at temperature 1. At a higher temperature, because the curve flattens and shifts out to the right, which I'm shading in red, you see a bigger area under the curve. That means more particles have activation energy, or an energy greater than the activation energy. And so you'll have more effective collisions, and so the reaction rate will be faster. So what is the nature of the relationship between temperature and reaction rate? And why does reaction rate change? If we think about the differential rate law, which just says rate is equal to K times concentration of reactant raised to some power, M let's call it, what would have to change here in order for the rate to increase? Well, the concentration doesn't change just because it's hotter out, nor does the order change. The only thing that can possibly change to make the rate faster is K. So there has to be a relationship between K and temperature. When you plot out that relationship using absolute temperature on the x-axis and K on the y-axis, you find out that it isn't a linear relationship. So one of the things that chemists used to like to do back in the old day when they're discovering these laws for the first time was try to figure out what could they change these variables to make it linear. And when we look at this, you're going to find out something that's analogous to an equation you've already seen. It turns out that when you plot the inverse of absolute temperature against the natural log of K, you finally get a straight line. And here we see this for a particular reaction of some kind. The numbers aren't important here. What's important is that when it's inverse of absolute temperature versus natural log, you get a straight line relationship. Well, thinking about the generic form of a line, y equals mx plus b, let's try and fit some variables from this graph to the equation of a line. On the y-axis we have natural log of k, and we've got a slope, which we're just going to leave for now. On the x-axis we're plotting 1 over t, and then we've got a y-intercept, some constant number. It turned out that the slope of this line is minus the activation energy over r. There's r again, shows up in our equation. So this equation, which is called the Arrhenius equation, says the natural log of k is equal to minus Ea over r times 1 over t plus a constant of integration, or a y-intercept. It might be handy to get rid of the y-intercept and get a 2-point form, and we can do that, but you should probably already recognize what it might be, because this is completely analogous to the Clausius-Clapeyron equation, where k's would be replaced by p's, and the slope, instead of being delta HVAP over r, is minus Ea over r. So the 2-point form will be natural log of k1 over k2 is equal to minus Ea over r times t2 minus t1 over t1 t2. So this can be used to solve problems where we know a temperature and then a second temperature, and we know the k at one temperature and we want to know the k at the other. Or if we know 2 k's and 1 t, we can find the second t. Or if we know all the k and t variables, we can predict what the activation energy will be for the reaction. So here's an example. Here's a reaction between CH3I and hydrogen iodide to produce methane and iodine. We have 2 pieces of information about k and t. We have a temperature corresponding to a k value and another temperature corresponding to a different k value. These are supposed to be absolute temperatures, so let's convert right away. 350 degrees C is 623 kelvins, and 400 degrees C is 673 kelvins. So there's a 50 Kelvin difference in temperature. Well, since this is a relationship between k's and t's, the Arrhenius equation that we just saw should be the way to solve this. What we want to find here is Ea. Let's get to a different workspace and practice this. So here's our basic Arrhenius equation. Natural log of k1 over k2 is equal to minus Ea over r times t2 minus t1 over t1 times t2. What we're trying to find here is Ea. That's our goal. So let's solve for Ea. The natural log of k1 over k2 times t1 t2 over t2 minus t1 would be equal to minus Ea over r if I just divide both sides by the temperature containing term on the right hand side. So then I'll multiply both sides by r, and I'll get this. I'll actually multiply by negative r minus r times natural log of k1 over k2 is equal, or times t1 t2 over t2 minus t1 is equal to Ea. So now I just need to plug some numbers in here. So minus 8.314 joules per mole Kelvin, that's R that we're using, times the natural log of 3.2 liters per mole second divided by 23 liters per mole second. I'm not putting units in because they cancel out, times 623 kelvins times 673 kelvins over 673 kelvins minus 623 kelvins. See what happens to units. We're going to have Kelvin squared in the top, kelvins in the bottom, so that'll leave 1 Kelvin in the top. That'll cancel with these kelvins here. So all kelvins are going to cancel out. So our unit will be joules per mole. So activation energy should be energy. Will come out in units of joules for every mole. When I work this out, I get that Ea is equal to 140,000 joules per mole, or I could say 140 kilojoules per mole if I wanted to use a smaller number. I'm going to show you another way to do this using a feature of your graphing calculator that many of you may not be familiar with. called the solver. Your graphing calculator has the ability to solve equations that have several variables in them for whichever variable you're interested in solving for. This feature is called the solver. The first thing we're going to do is take the Clausius-Clapeyron equation and turn it into terms that are compatible with how the TI graphing calculator recognizes them. So let's take a look at our calculator. How you get to your solver is you push the math button, and then option 0 actually is the solver. You may already have something in your solver. If you do, you just arrow up until you have something that looks like this. 0 equals something. And if there's anything in there, just hit clear and it'll disappear. Now, the equation solver wants every equation in the form 0 equals the rest of the equation. So let's convert the Arrhenius equation so that it fits that mode. Let me get the calculator out of the way for a sec. And now let's start out by writing down the Arrhenius equation. It's natural log of K1 over K2 equals minus EA over R times, and I'm going to use the simple form, 1 over T1 minus 1 over T2, because I think that'll work best for the calculator. Now, if I just subtract natural log of K1 over K2 from both sides, I have it in that 0 form. So 0 equals minus EA over R times 1 over T1 minus 1 over T2 minus the natural log of K1 over K2. Now, in terms that the calculator can understand, because it can only do one-letter variables, I'm going to change T1 to just T, and T2 I'm going to use U, the next letter in the alphabet. And I'm going to do the same thing for K's. I'm going to make K1 K, and then I'm going to make K2 L, the next letter in the alphabet. So this equation becomes 0 equals minus, and I can't use E, A, so I'll just use E, E divided by R times 1 over T minus 1 over U minus the natural log of K over L. And I'll key that into my calculator, and then I'll show you how to solve with it. Pull my calculator back up, and I'll key in all this information. So negative key, and then alpha E divided by alpha R times, throw a parenthesis in here, 1 divided by alpha T minus 1 divided by alpha U minus the natural log of alpha K divided by alpha L. Close the parenthesis. Now when I hit enter, watch what happens. I get a list of all the variables in my equation, and then this last line says bound. I'm going to set bound to look for answers in the range that I know my answer should be. EA should end up being a positive number, so I'm going to key down to the boundary, put in 0, and then delete all the rest of the digits before the comma. So now it's going to look for an answer between 0 and positive 1 to the 99th. EA is a number that I don't know, so I'm going to leave that just what it is right now. R is 8.314 for some reason. That's already in my calculator. But if it wasn't, I would just key in 8.314. T1. Our T1 was 623 kelvins, so I'll just put that in here, 623. T2 was 673, so 673. And if I had this in Celsius, I could have just done this. Just show you this. 400 plus 273, and make the calculator figure out that that's 673. So what's K? Well, K was K1, that was 3.2. And L was K2, which was 23. Now that I have all this information in here, I'll just key back up to the variable I'm trying to solve for, which is E. And then I'm going to hit the alpha button, and the green writing up above the enter key is solve. So I'm going to hit alpha, enter, and it will solve this equation for EA. Thinks for a little while, and then it returns my answer. Now, it doesn't know anything about significant figures, so I have to be smart enough to know that I should round this off to 140,000. But that's how you can use the solver. This could be used with the Clausius-Clapeyron equation, obviously, and it can be used with this equation, which is analogous to it, or anything that you want to solve that has multiple variables. It really speeds things up. On the calculator allowed portion of the AP exam, you can use your graphing calculator, and you can use anything that you have in the solver or any programs that you have. So this is probably a technique that could save you some time in the future. Well, in our next video, we're going to talk about how do reactions actually take place at the submolecular level. Sometimes the collisions don't seem like they'd be very likely the way the reaction is written, and often that's the case. And so there's another pathway that's taken by the reaction, different kinds of collisions that maybe don't show up in the overall balanced chemical equation. That's called a mechanism, and that's our topic for next time.